Okay, we had an exam last week. So I saw your grade. You did well. Everybody, I think, did well. Okay. But we have another second midterm. We'll take 2 midterm in this course, 2 midterm and 1 final. So second midterm, I'm thinking it will be the beginning of April, first week of April. Okay. Later we'll decide that which date will be. Okay. Before we start, do you have any questions or comments regarding our exam as well as our last class? Okay, if you do not have questions, we can start our today's sessions. In our, we have already started the CP scheduling algorithms, and so far we learned the shortest job first algorithms or SJF, and then shortest remaining time first or SRTF algorithms. And in our last class, we have studied also the FCFS, means that first come, first serve scheduling algorithms. And among these algorithms, we know that SJF is non-preemptive scheduling algorithms, and SRTF is also this is preemptive scheduling algorithm, SRTF, and you know the first come first serve or FCFS is also a non-preemptive scheduling algorithms. Okay. Every algorithm, it has some properties. You already know about this. For example, FCFS, we have discussed in last class that the process which comes first or least arrival time will be scheduled first. This FCFS, it's actually similar to its algorithm's name. Okay, it works like a FIFO, first in, first out. Okay, and it is non-preemptive scheduling algorithms. And also it is not a priority-based scheduling algorithms, FCFS, because the arrival time, it is not a property of a process. Previously, SJF and SRTF, it's the operating system is schedule algorithms depending on the burst time or execution time. You know, this execution time is a kind of properties of a process. But arrival time, it is not a arrival time. It is not a property of a process. So it is just the just whenever a process comes inside the RAM, it depends on and serve this process. Okay, it is simple. So it is not a priority based scheduling algorithms. Okay, so let's see one example for FCFS. Before let me share my screen from my, before I start, let me share my screen. Okay. Okay. Let me stop my video, hopefully, because I met from two PC. Currently, I'm not. Okay. iPad. Okay. Let me think. Let me see. Let me show you one example from FCFS algorithms. And you know that FCFS or first come first serve scheduling algorithms. Okay, it is first come first serve FCFS. Okay, FCFS algorithm. So let's see how it's work. Let's assume that we have total 5 processes. This is process ID. We have total 5 processes. Let's say process P1, P2, P3, P4, and P5. This is the process ID P5. Okay, this is process ID, and we know the arrival time of a process, and we know the execution time or burst time of a process. So let's see, arrival time of a process P1 is 0, Simple 1, 2, 3, 4 units of time. And the execution time of process P1 is 4. The process P2 is 3. Process P3 1. And process P4 needs 2 units of time. And process 5 also needs 5 units of time. Okay. This is the execution time of the process. Okay. Now let's see that how our FCFS works. Okay. Now let's see how FCFS algorithms work. We'll complete that. First, we have to complete the Gantt chart. Gantt chart. Let's draw in here. Let's say, sorry. We have total 5 processes. Okay, 5 processes. I should draw in here. So this is the starting time 0. This is Gantt chart. Okay, this is starting point 0. At this starting point 0, which process inside the RAM from this table? This is a table. P1 arrives at time unit 0. So P1 is already started inside the RAM, but P2 will be arrived at time unit 1. So only P1 inside the RAM. So your operating system will schedule the process P1 to the CPU, and P1 will be start execution. So at 0 time, P1 process will be start. Okay, starting execution process P1, and then P1, since it is non-preemptive scheduling algorithm. So once your OS schedule a process to the CPU, it's never stop until completes its execution. Okay, so process P1, it needs total 4 units of time. So till 4 it will execute. Okay, and after that, at time unit 4, how many process inside the RAM? You know, this is time unit 4. At time unit 1, P2 is here, P3 arrived at RAM. At time unit 2, P3, P4 at time unit 3, and P5 also time unit 4. So you see now all processes are now currently inside the RAM. So from here, which one will pick will pick by your operating system? The process that arrives first inside the RAM. So from here, P2 arrives first. It is it is actually very simple. So P2 will serve first, and P2 takes 3 units of time. So it is 7, and then which process will arrive? Then which one will pick? Then P2 comes first. P3 after P2, then P3 will be scheduled. And it takes 2 units. Sorry, 1 units of time. So it will be here complex execution. Then P4, and P4 needs 2 units of time. 2 units of time. So it is now 10. And next P5 will be scheduled. P5 will be scheduled, and P5 needs 5 units of time. Okay, 5 units of, so 10 plus 5 equal to 15. 15. 0 till 15. This will be the actually schedule length for these algorithms. Now we can compute the some other parameters like completion time, turnaround time, also the waiting time as well. Okay, you can calculate. Let's extend this table. Okay, so now let's calculate in here completion time, also turnaround time, and next is last one is the, let's say, waiting time, WT, waiting time. Okay, from here completion time you can calculate from this Gantt chart. So P1 completed time unit 4, it is also easy. P2 completed time unit 7, P3 completed time unit 8, and then P4 at time unit 10, and P5 completes at time unit 15. Okay, it's the completion of time, and then turnaround time. Turnaround time is nothing but completion time minus arrival time. Okay, so CT is completion time, arrival time is 18 here. So 4 minus 0 is 4. 7 minus 1 is 6. 8 minus 2 is 6. 10 minus 3 is 7, and 11 here. Okay, this is the turnaround time for each process. And then next, calculate the waiting time. Waiting time, you can know, the turnaround time also defined as execution time or burst time plus IO time plus waiting time. Okay, waiting time. These are the three parameters. Is nothing but the turnaround time also. Okay, so from here, what you can do, what you can calculate, you can let's consider the no process goes inside for IO operation. So IO is 0. Let's consider IO is 0. No process actually use the IO, any IO devices. So IO time will be the 0. So in this case, waiting time is nothing but we already know about the turnaround time minus execution time. Okay, execution time. So 4 minus, here it is, execution time is 4, so waiting time is 0. 6 minus 3 is 3. 6 minus 1 is 5. 7 minus 2 is 9, and then 11 minus sorry, I made a mistake. Let's check. Oh, okay, waiting time. 7 minus 2 is 5. And then 11 minus 6 is 11 minus 5 is 6. Okay, this is 5. Right. Okay, this is the turnaround time, waiting time for also if you apply the first come first serve algorithms. Okay, this is pretty simple algorithms. The process that comes first inside the RAM, your operating system will schedule these algorithms. Okay, and next one is, okay, so these are the first 3 or 4. We learned total 3 algorithms, and we learned some 3 or 4 algorithms in next. So before we start these 3 or 4 some other algorithms, let's see some comparison analysis between these 3 algorithms. Okay, between these 3 algorithms, that which works better and which works worse, kind of like this. Okay, okay, so we already know the 3 different algorithms. One is LJF, shortest job first scheduling algorithms. We compare this. Also SRTF, shortest remaining time first scheduling algorithms, and then also another, we know the FCFS. Okay, we currently run the FCFS algorithm. These are the 3 algorithms we know already. Okay, so from here in comparison analysis, first you know already what is the starvation problem in our memory management or memory, when we schedule for when we learn about the computer's memory and how we schedule a process inside the memory. That time we learn about the starvation problem. Okay, starvation problem. Sorry. Starvation problem. Okay, starvation problem. Also, when we learn the starvation problem, that time we already mentioned that I actually told you that if you consider any priority-based algorithms, it may suffer by the starvation problems. So let's actually reanalyze this. What is the distribution problems? Let's say you have some processes that want to schedule by the CPU. Let's say process P1, P2, and P3. Okay, P3 schedule will be scheduled to the CPU by your operating system. And you know the LJF and SRTF, these are the priority-based scheduling algorithms. Okay, it's in case of LJF, it will schedule a process that has the lowest execution time or burst time, but it is non-preemptive. This is non-preemptive scheduling algorithms. Okay, and SRTF also scheduling priority-based algorithms. SRTF also priority-based algorithm, but it is preemptive scheduling algorithms. Okay, preemptive scheduling algorithms. Now, what is the starvation problems? You know that starvation problem means that a process may wait for a undefined indefinite time. Okay, we don't know the time when a process may get the CPU. This is indefinite time. Okay, it is not a defined. We cannot define the process. So how the distribution problems arise in this situation? Let's say our CPU RAM. This is the RAM. It contains now total 3 processes. And your operating system is currently scheduling the process P2 or let's say P3 because its priority is higher, and then P3 is currently start execution. So start execution. Once it's complete, then again new process may be P4 inside the RAM. Its priority is higher than P2 and P3. Also, then P4 will be served by the operating system. Anything, if you consider the SJF or SRTF algorithms, okay. Let's say P3, it has the lower burst time or execution time than P1, P2. So P3 will get the priority, and P4 arrives. It also contains the lower burst time than P1, P2. So P2 will be scheduled by the CPU if you use the SJF and SRTF algorithms. Okay, and it gives the priority for lower burst time. Okay. And then again, let's say P5 will arrive, and P5 will be executes in here. Okay, so you don't know that when the process P1, P2 will get the CPU. Okay, this is the starvation problems. A process can wait a undefined time. Okay, so this is the starvation problems. Also, if you consider any priority-based algorithms, it's suffered by the starvation problems. Okay, that is SJF and SRTF may suffered by the starvation problems. Okay, and but if you consider the FCFS is not a priority-based algorithm. Okay, it is not a priority-based algorithm. Does it suffer the starvation problem? Answer is no. It doesn't. It's never suffered by the starvation problems. Okay, no starvation problems for no starvation problem for FCFS. Okay, because it is not a priority-based algorithm. It is simply schedule a CPU, the process which comes first. Okay, it doesn't think about the execution time or some other priority of a process. It's never think about any priority. Okay, P2, P3, let's say P4. Okay, the process P1 comes first, so it will serve first, then P2, then P3, then P4. Okay, if it's arrived in this order. Okay. Okay, so FCFS, it's never suffered by the starvation problem because it is not a priority-based algorithms. Otherwise, on the other hand, SJF and SRTF may suffer by the starvation problems. Okay, because it is the priority-based scheduling algorithms. Okay, so these are the some comparisons for some advantage or drawbacks for three algorithms. Not we are not complete yet. We have some others issue for others algorithms. Let's say what is some others problems may arise if we use some this type of algorithms. Let's see some another problems is called the now we learn the starvation problems. Now we'll see the another term is called the convoy effect. Convoy effect. Okay. So what is the convoy effect? Let me define it. A convoy effect is nothing but a smaller process. A smaller process means that a process with very short execution time. Okay, a smaller process is nothing but here a smaller process means the process with a very short execution time. Okay, this is we consider here the smaller process, not the size. Okay, a smaller process means a process with a very short execution time, waiting for a big process to get off or release the CPU. Okay, so this is called the convoy effect. Means that a very short execution time. A process need very short execution time, but this process may wait for a long time to get off the CPU, get off or release the CPU. Okay, this is the convoy effect. Okay. Okay, let's see one example. Let's see, you have two process. One needs P1 and P2. Okay, this process needs let me clear it for you, that you can understand. This one P1 and P2. This process needs 10 nanosecond execution time. Also, this process needs, let's say, 2000 nanosecond. Okay, execution time for 2000 nanosecond, and this process needs only 10 nanosecond. Okay, so if you consider the if you think about the FCFS algorithms, if you consider this first come first serve scheduling algorithms, let's say process arrived in this order. P1 comes first inside the RAM, then P2. Okay, then P2 process comes in this order. Okay, if you consider the FCFS algorithms, what it does, it never see anything. It never see any execution time or anything. It will see that P1 comes first inside the RAM, so it will give the CPU for P1. Operating system will schedule the process P1 for CPU. Also, it is non-preemptive algorithm, so it will complete its execution. P1 will complete the execution, and it takes total 2000 nanosecond time. But and this time also in the also let's after 1 nanosecond process P2 inside the RAM, it takes only 10 nanosecond of time. Then after completing this process, then your CPU your operating system will schedule this process P2. Okay, P2 inside the RAM. So from here you can see that this is small. This process needs very small amount time for to finish its executions. Okay, to finish its execution, but due to the actually a high due to the long the wrong runtime of due to the actually high execution time or large execution time for a process, your smaller process or very short execution time a process requires, this process needs to wait for a long time. Okay, so this is the combo effect. So from here you can see that your FCFS algorithms may suffer by this combo effect problems. Okay, FCFS of course suffered by this combo effect problems. Okay, combo effect. convoy effect problem for FCFS. Okay, let's check the SJF suffer by convoy effect or not. Okay, SJF. Okay, SJF means that the shortest job first. Okay, shortest job first is nothing but it depends on the execution time, the process that require actually lowest execution time. Okay, this process will be scheduled by the operating system if you consider the SJF algorithms. Okay, let's say you can consider, let's say we have total two process P1 and P2 inside the RAM. P1 comes first. Let's say if we consider this at the 0 time, P1 comes. Okay, P1 comes, and then P2. Then P2 comes at let's say 1 nanosecond in here. At 0 time, you need P1 inside the RAM, and after 1 nanosecond later, P2 inside the RAM. So if you consider the SJF algorithm, SJF is nothing but 0 time unit. There is no process apart from the P1 inside the RAM. So it will schedule, your operating system will schedule the process P1 because there is no other process inside the RAM. At time unit 0. Okay. So which process will schedule by the CPU? There is no other choice. So it will schedule the process P1. Okay, it will schedule the process P1 inside the CPU, and after 1 nanosecond later, the process P2 also inside the RAM. So you know that SJF is non-preemptive algorithms. Okay, non-preemptive algorithms. So once P1 is scheduled by your operating systems, it's never your process execution never preempt or never stopped by the CPU, even though the lower execution type process inside the RAM. Okay, so it is non-preemptive. P1 is already scheduled by operating system, so P1 completes its execution first, and then your operating system can schedule the process P2. Okay, in that case, you see that if you consider this SJF algorithms, it may suffer by the convoy effect as well. Okay, if you consider the SJF algorithms, okay, it may suffer by the convoy effect as well. But you can consider one more step for better understanding. Let's say we have another process. Sorry, here you see. Let's say this is P2. P2 need, let's say 1000 nanosecond, just for an example. And also P3 another process, it needs a 2 nanosecond. Okay, 2 nanosecond. Okay, so if you consider this FCFS, first come first serve, so it will schedule the P1 first. It takes 2000 nanosecond for a complete execution, and by this time, let's say after 1 nanosecond later, this P2 P3 inside the RAM as well. So what's it will do? Then your FCFS will then next time after completes the execution of process P1, your FCFS will schedule nothing but the process P2, because P2 comes inside the RAM first before P3. So P2 will be scheduled. It takes also 1000 nanosecond, and then it will schedule the process P3. Okay, P3 it takes only 2 nanosecond. Okay, from here you can see that small, actually this takes very small amount of time for execution. So this process needs to wait a very long amount of time. Okay, if you consider this FCFS. But in case if you consider this SJF, in that situation, what it does, how it works. Your operating system at first will schedule the process P1, and it is non-preemptive. So P1 will complete its execution. Okay, P1 is complete its execution. It takes 2000 nanosecond. Okay, and then next when it's actually again go for schedule a process. What it will do with SJF? SJF will take the process pick the process that needs the lowest burst time. Then it will schedule the process P3. Okay, it is the process P3 because P3 needs the lowest burst time. Okay, then P3 will be executed. Okay, Okay, so you know that in convoy effect for FCFS could be very serious, but for SJF, even though it may suffer by this convoy effect, in a previous example we see the 2000 also, then 10 nanosecond, SJF suffer by this convoy effect, but it may not as severe as the FCFS algorithms. Okay. Okay. So do you have any questions or comments for comparisons or any comparison analysis or for convoy effect? Okay, so let's see the what if we consider the SRTF, our last algorithm that we have to check the SRTF. Before I start SRTF, let me clean it again. Little bit clean it again. Yes. Okay. Now let's see. In this algorithms need this process need 2000 nanosecond. Also, yeah, this process need 10 nanosecond. Okay, 10 nanosecond. Okay. Okay, from here you can see if you consider the SRTF algorithms, SRTF is nothing but a primitive version of SJF. Okay, it's primitive version of SJF. Let's say process P1 comes at time unit 0 and process P2 comes at time unit 1. Okay, 1 inside the RAM. Okay, so how your SRTF algorithms will work? SRTF will at time unit 0 there are no other process except P1. So what's the operating system will do? Operating system will schedule the process P1 first for the CPU. So P1 will start execution, and then what's your operating system after 1 nanosecond? After 1 nanosecond, there are two processes. Here is each comes at 0. Here is comes at 1 nanosecond. So after 1 nanosecond, your algorithms operating system will check this how many processes inside the RAM. Okay, from here it will see that the process P1 and P2 inside the RAM. So P1 still need 1999 nanosecond. Sorry. Okay, and then also these algorithms need this process need only 10 nanosecond. Okay, from this which one it will pick? It will pick the lowest remaining time or lowest burst time is process nothing but process P2. Okay, so it will your operating system will what it will do? It will schedule the CPU for process P2. Okay, process P2. If you consider the SRTF algorithms, okay, it is schedule the CPU for process P2 because it takes only 10 nanosecond of time. Okay, 10 nanoseconds. So it will take this 10 nanosecond and it will complete this execution 11 nanosecond in here, and then again your another process P1 completes its execution. Okay, completes execution. So 2010. Okay, nanosecond. Here it completes its execution. Okay, so now let's see that it's if you consider this SRTF algorithms, if you consider the SRTF algorithms, it never suffer the convoy effect problems. Okay, it's never this algorithm never suffer by the convoy effect problems. Okay. Okay. So also, what is the actually effect of convoy actually problems? What is the actually these disadvantage for convoy effects? Let's check some other properties for convoy effect problems. And first one is an algorithms with a convoy effect problems may lead to large waiting time and higher turnaround time with an algorithms without a convoy effect problems. Okay, without a convoy effect problems, the algorithm is the algorithm that doesn't suffer by the convoy effect problems. Okay, Yeah, if your algorithm is suffered by the combo effect problem, a process needs to wait a long time. Of course, here it is very obvious. Here you can see that this process needs to wait 2000 nanosecond of time to get the CPU. Okay, it takes the long waiting time. Also, if your waiting time is long, so for this process, turnaround time will be higher. Okay, you know this turnaround time is nothing but waiting time plus IO time plus burst time or execution time. Okay, so if your waiting time increase, then your turnaround time will be also increased. Okay, so this is the one of the problems. And also you see that another thing is that throughput. You know that throughput is nothing but the number of process executed per unit of time. Okay, number of process executed per unit of time is nothing but number of process but one schedule length. Okay, schedule length. Okay, number of process executes per unit of time. So if you consider the FCFS algorithms, let's say in here, let me open a new. If you consider new page, so if you consider the FCFS algorithms, this is your CPU, this is the memory, and let's say P1, it needs 2000 nanosecond of time. Let's say P2, also it needs, let's say 1500 nanosecond of time, and then P3 needs 10 nanosecond, P4 needs 2 nanosecond, and it's a P5 needs 1 nanosecond. Okay, if you consider the FCFS algorithms, let's say after 2000 nanosecond, throughput is nothing but the number of process executes per unit of time. If you consider this P1 FCFS algorithms till 2000 nanosecond. If you look at in here, the throughput is 0. Still, throughput is number of how many numbers process are completed per unit of time. If you consider, look at in here, there is no process is still completed. Okay, so still throughput is 0. After 2000 nanosecond later, you will find that throughput is 1. Okay, if you consider the FCFS, and then P2 will be scheduled. So after 3500 nanosecond later, you will see this throughput is 2. Okay, let's complete the 2 processes in this second. Okay, but if you consider this SJF, SJF algorithms, in case of this is FCFS, first come first serve algorithms, and this is SJF, shortest job first algorithms. So at first time there is no process, so your operating system will schedule this process P1, and then it will start processing. So in 2000, it is non-preemptive, so it will it executes till 2000 nanosecond process P1. So here also you can see that there is no throughput, still no process completes its execution. So after 2000 nanosecond later, your operating system will check this which process needs actually shortest burst time. That one will execute. So this process needs the shortest burst time. So P1 will be, P5 will be scheduled, and it takes 1 nanosecond. And from here, P4 will be, so it will be 2001. 2001 nanosecond, because it needs 1 unit of time. 1 nanosecond of time. As you consider this nanosecond, here 1 nanosecond, then P4. P4 needs 2 nanoseconds, so 2003 nanosecond in here. So in here, if you look at in here, throughput is 1, 2, 3. Okay, 3 throughput. Okay. Obviously, here is till 3500 nanosecond, your throughput is only 2. Here is 2003 nanosecond, your throughput is already 3. Okay. If you go more, and 2013 nanosecond, your process P3 also complete. Okay, P3 also complete. So here you can see this throughput is 4. But also, if you consider the SRTF, SRTF will give you the more throughput than SJF because in let's say P1, it completes 1 nanosecond. Here is 1 nanosecond, and then it will execute after 1 nanosecond all processes inside the RAM. So it will execute the P5. P5 after 2 nanosecond, you will see that one process already complete, and then it will execute the schedule this one P4. P4 needs 2 nanosecond, 4 nanosecond, 2 is complete. 2 processes already completes its execution, and after 14 nanosecond, it takes P3. P3 needs 10 nanoseconds, so 4 plus 10 is 14 nanoseconds. So P3 is completes its execution. So after 14 nanoseconds later, you can see already throughput is already 3. Okay. So from here you can see that throughput of SJF and SRTF algorithm much higher than the FCFS algorithms. Of course, throughput SRTF algorithms much better than the SJF algorithms as well. Okay, SRTF should be greater than SJF throughput. Okay, okay. If throughput is high, means that your computer is more faster to execute a process. For any given time, if you look at check the how many processes actually completes by your operating your CPU. So better throughput means that your computer is actually work faster. Okay, work faster than the lower throughput. Okay, so this is another, we can say, disadvantage for the FCFS algorithms. It affects by the combo effect. Also, throughput is very lower than the SRTF, also SJF algorithms. Okay. Okay, so these are the some comparison of 3 different algorithms that we have already learned, and our next is we'll see some others language, others algorithms that are kind of opposite of that we learned already. One is the shortest job fast. Now we'll see that how actually longest job fast scheduling algorithms work. Means that kind of opposite of shortest job fast scheduling algorithms. Okay, if you consider the longest job fast scheduling algorithms, let me here I write in here. Okay, let me turn on my pen. Okay, yes. Next we want to see the algorithm names, the longest job fast, or LJF. LJF scheduling algorithm. Okay, longest job fast scheduling algorithms. So it is kind of opposite of SJF algorithms. From this name, you can understand among the arrived processes, processes with the longest execution time or burst time will be scheduled first. Okay, if your operating system consider the LJF scheduling algorithms. Okay, it will schedule the largest execution time or burst time process. Okay, in it is opposite of SJF. So it is also a priority-based algorithm. From here, you can see that your operating system will schedule algorithms that needs the largest or highest execution time or burst time. So execution time and burst time is a property of your process. Okay, so it is a priority-based scheduling algorithms. Also, similar as SJF, it is also non-preemptive scheduling algorithms. Okay, it is also non-preemptive scheduling algorithms. Okay, also if you consider so from here what is the actually three properties for it is schedule process with largest schedule time or burst time will be scheduled first. Okay, largest burst time or execution time will be scheduled first. Okay, second is this is priority based algorithms. This is priority based algorithms. And third one is this is non-preemptive scheduling algorithms. Okay, these are the three properties for the LJF scheduling algorithms. And from here you can guess, you can also know that this is a priority based algorithms. So what would be the problems if it is priority based algorithms? What will be the problems for LJF? First problem will be, of course, starvation problems exist. It is priority based algorithm, so starvation problems here also exist. Next is this is longest job first scheduling algorithms. So we learn only the convoy effect. So here is convoy effect problem also exists because it will schedule the longest job first. Okay, so convoy effects problem also exist here. Third one is would be if it is like this convoy effect problems, then throughput will be very less. Okay, you already know throughput is very less. Fourth part will be this part. Okay, this part it says this difficult to implement. Okay, I didn't talk about the difficulties of implement. Let me give you some quick overview for how it is difficult to implement. So if you consider the SJF, let's consider SJF, SRTF, and also FCFS. Okay, FCFS. Okay, these are the three algorithms. So you know that these two algorithms needs to calculate the lowest burst time or execution time. Okay, minimum burst time or execution time. This algorithm needs to calculate a process process burst time or execution time. Okay, but in practical, actually, in real life, it is very difficult to calculate or calculates the total burst time required for a particular process. Okay, so in practically these two algorithms is difficult to implement. So in here LJF, it also depends on the largest burst time. Okay, here also your operating system, if your operating system use this type of algorithms, here also your operating system needs to calculate the burst time or execution time. But this time, burst time or execution time, it's very difficult to calculate or predict. So that is the reason it is very difficult to implement. But if you consider these FCFS algorithms, here doesn't equate to, you don't equate to calculate any burst time or execution time. It is very simple. The process that will come first inside the RAM will be scheduled by your operating system. Okay, here you don't require to calculate any burst time or execution time. Okay, this is very simple algorithms, so you can implement easily if you consider this FCFS algorithms. Okay, instead of SRTF and SJF. Also in case of LJF, here also you need to calculate also the burst time, so it is very difficult to implement. Okay, these are difficulties, some difficulties for LJF and SRTF algorithms. Now let's see one example for largest job first scheduling algorithms. Let's say we have total let's say total 5 processes. P1. This is the process ID. Here is process ID. This is arrival time of a process. This is the execution time or burst time. Okay, here let's say P1 process ID, P2, P3, and P4. Let's stick it this 4 process. It's arrived at 0, 1, 2, 3 time unit, and process P1 needs the 10 nanosecond. The process P2 needs, let's say, 20 nanosecond. Process P3 needs 5 nanosecond. Process P4 needs 50 nanosecond. Okay, and 50, that's 30 nanosecond. Okay, now let's calculate the. Let's check the Gantt chart for if you consider this LJF scheduling algorithms, longest job first scheduling algorithms. Gantt chart, we consider here. Draw the Gantt chart for this process. At first time unit 0, because this is non-preemptive. I already mentioned this is non-preemptive scheduling algorithms. Okay, non-preemptive, because this is very important. Okay, you need to know that which algorithm is preemptive, which algorithm is non-preemptive. Okay, also in your exam, okay, take this note as well. This is preemptive and non-preemptive. Also, you need to know about the clear idea that what does mean the primitive as well as the non-primitive. Okay, so this is the Gantt chart. If we start with time unit 0, at time unit 0, the process only process P1 inside the RAM. So there is no other choice for your operating system to schedule a process. So here is nothing but process P1 will be scheduled by the operating system, and P1 takes total, let's say total 10 nanosecond of time. Now, not time unit, on time you need to define this nanosecond. Okay, nanosecond. Okay, nanosecond. 10 nanosecond of time. So once it's scheduled for a CPU, it takes total 10 nanosecond. Total 10 nanosecond. It never preempted. It's never preempted by the CPU because it is non-preemptive algorithms. It's never stopped. Okay, until it's finishes its execution. So after 10 nanosecond later, what will you find? All process inside the RAM. Okay, so last process comes at 3 nanosecond, 3 time unit or 3 nanosecond later. Okay, let's say. So this algorithm, this process takes total 10 nanoseconds. So after 10 nanoseconds, every process inside the RAM, P2, P3, P4, and P1 already completes its execution. P1 already completes the execution. Now, among this process, which process will be scheduled by the operating system? Here, process P2 needs 20 nanosecond, process P3 needs 5 nanosecond, and process P4 needs how much time? 30 nanosecond. Okay. So highest time needs for process P4. So process P4 will be scheduled by the CPU. So P4 here is process P4 comes and it takes 30. It needs 30 nanosecond. It is non-preemptive, so it's never preempt or never stop. So it will complete the execution at 40 nanosecond. Here is time, and then which process will now process P1 and P4 done. We have only two process inside the RAM. From here, P2 needs 20 nanosecond and P3 needs total 5 nanosecond of time. So which process will schedule? Process nothing but process P2, because it needs 20 nanosecond. So 20 here is 60 nanosecond. It will complete its execution, and finally the process P3 will be scheduled, and it needs 5 nanosecond. Okay, 5 nanosecond. So 65. It will complete the execution. Okay. So from here you can calculate also. It is very easy. You can calculate the completion time as well as the turnaround time. Okay. Let's say calculate CT, how it looks like. Let's see. In CT is nothing but the arrival time minus completion time. From here you can see that P1 completes at time unit 10. Sorry. Here it completes at time, it completes time at time unit 10. And P2 completes at when? In here. P2 completes time unit 60. And P3 completes at time unit 65. You see 65. Waiting time is very high. Huh? And then P4 completes at time unit 40. 40. Yeah, 40. Okay. So now let's see what is the turnaround time for this process. Turnaround time is nothing but the completion time minus arrival time. So here is 10. Here is 60 minus 1 is 59 nanosecond. Waiting time is very high for a process. 65 minus 2 is 63. And here 40 minus 3 is nothing but 37. Okay. This is the turnaround time for a process. Also, you can calculate the waiting time as well. Waiting time, if you consider the IO is 0, so waiting time is nothing but turnaround time minus execution time. Okay, execution time or burst time. Okay, execution time or burst time. Okay, now let's see what is the turnaround time 10 minus burst time is 0, so it's waiting for a 0 time unit. And then 59 minus 20, so it's wait for 9 and 3, 39, and 60 63 minus 5. Here is 63 minus 5, 58, and here is 37 minus 30 is 7. Okay, this is the waiting time for this process. Okay, waiting time for this process. So if you consider the longest LJF or LJF, longest job fast scheduling algorithms. Okay. Okay, so these are the this is all for this LJF. So we have another algorithms. It's kind of similar of SRTF. We know that SJF, and then SRTF. Here we already learned the LJF. We have another algorithms is LJF. SRTF. Okay, LRTF. It's nothing but primitive version of LJF algorithms. Okay, or opposite of SRTF. Okay, just opposite of SRTF. Okay, this is that one is opposite of SJF. LRTF is opposite of SRTF. Okay, SRTF is longest remaining time first scheduling algorithms. Okay, it is nothing but primitive version of LJF. Okay, uh, uh, before we start this algorithm, do you have any questions or comments so far? Okay, if you do not have any questions or comment, we almost running out time. So let's start LRTF in our next class. Okay, so good evening everybody and see you in next class.